So, good morning, everyone. It's a pleasure to see you all this bright and early today for the webinar session of evolution of FPGA technologies. So, before we go into the session, like there is a pool going on, so I encourage everybody to take a part of this pool. So, I extend a warm welcome to every one of you joining us for this session. Allow me to introduce our esteemed speaker, Mr. Parish Joshi. So, Mr. Joshi holds a master's degree in IIT Bombay and a bachelor's degree from IIT Kanpur, and he is currently serving as a senior product architect at Siemens. And he brings a wealth of experience to the table. With the background in ASIC design, Mr. Joshi possesses extensive hands-on experience in complete SOC flow, including management of automobile designs. His skill sets encompasses various facts of front-end design, verification, synthesis, LEC, ECO, STA, and pre-silicon hardware and software validation, utilizing Unum and FPGA platform. Furthermore, Joshi contributes to academia as part of a lecturer at Pitspilani, Bangalore, where he imparts knowledge on hardware, software, co-designing, and embedded systems. We are truly fortunate to have Mr. Joshi with us today. I'm confident that these insights will enrich our understanding of FPGA technologies. Please join me in welcoming with a warm ritual welcome. So I will pass on the podium to Mr. Joshi. Please take it forward. Thank you.
Start. Greetings to everyone on the webinar page. Thank you very much for taking the time to participate in the webinar. And I'm hoping it to be a great session today. And I hope that a lot of learning, right, would come out of this, and team members would get a lot of inspiration to go through this path of FPGAs, right, in the future. So what we will be doing today, right, focus more on the evolution of the FPGA technologies. Okay, so the session will not be discussing about how to use an FPGA and all, but just an evolution, like the historical evolution of FPGA technologies. We will also be covering a lot of topics on a little bit, right, on how things got developed over a period of time, right, and a sneak peek into what I see as the future, because we cannot see the future, but one sneak peek into what we think are, are the things that we can at least foresee in the next few years. Right? So the way we will try to put the agenda is, again, starting from very humble beginnings towards, gradually going to a modern FPGA world, right? The next one we say is the economics part of it. Okay, so how the economics of FPGA involved, because there are a lot of competing technologies that are there, a lot of people talking about SOC, talking about ASICs, and then this FPGA comes into the picture, memories, right? How the economics works, right, for the modern FPGA. We talk about that a little bit. Okay. We also talk about uses of CPLDs and FPGAs. Right. So, as you would have seen, right, I have not yet, given the acronym or the full form of what an FPGA is or what a CPLD is and so on, right? So keep that in your mind as of now. But we will be talking more about that, and at that time we will expand the meaning of these acronyms. The uses of CPLDs and FPGAs. Then we'll cover things on the development cost versus time between FPGAs and ASICs, right? Why FPGAs become so popular, kind of a thing, right? What kind of a development cost versus time benefits do the FPGAs give us, right? So we'll talk a little bit, we'll touch upon that. We'll briefly touch upon that, right, today. And again, right, I have not, given the acronyms for FPGA, what is an ASIC and all, right? So that in the coming, time, right, we will be touching upon it. Okay. Then we'll come to the concept, little bit more on the conceptualization of, how an FPGA works and so on, right? So we'll show the concept of a configurable logic gate. Okay, as you now start get the feel, right? There is something configurable in all this FPGA world, right? So we talk about the configurable logic gate and the basic FPGA block diagram. Okay, followed by what are the different flavors of FPGAs. So depending on different domains, different applications, a lot of different types of FPGAs have come into the picture, and we will start talking about the flavors of these FPGAs. Okay, what are the different types of FPGA devices and FPGA families that have come into the picture? Maybe we'll open up one or two, product data sheet tables from more prominent vendors and try to get a feel of, how the different flavors, different families of FPGAs are. Next, we'll get into the next level, right? Like I said, some hardening of processor subsystems into FPGAs, creation of SoC FPGAs, and some next level things, right? So what we will do is we'll go through the evolution, come up to what is current, and a little sneak peek, right, into what we, at least what I can see into the very near future, right? We don't know what the future holds for us, but at least some near future, right? So we start from the very humble beginnings, right? So I'm giving a 10-year cycle here, and I'm not expanding, okay, what happened in 41, 42, like that. I'm just saying, okay, the 1940s, right? The ENIAC computer, it used to fill, a large room, and largely it was made using vacuum tubes. Okay, so the thing to note here is the concept or the mathematic behind or the Boolean logic, right? Or all the the science behind creation of computers that already existing even before 1940s in the science world, right? And as soon as the vacuum tubes came, and then you start using the vacuum tubes in their the cutoff region and the saturation region, right? So that is where you get a logical 0 and a logical 1, right? So that gives rise to digital logic getting created and using a vacuum tube to do digital logic, right? Like AND gate, OR gate, inverters, some digital logic. And then you put digital logic together, create a Boolean function, and create a register. If you have something like a register, you can even create a finite state machine, right? So using vacuum tubes, right? These was all made possible. Okay, so it used vacuum tubes. It also used electromechanical devices, large discs, okay, and magnetic tapes and so on. Right. So ENIAC computer used vacuum tubes. Okay, in the 1950s, right, there was an entry into that. So what earlier used to be a very complete big room consisting of vacuum tubes, right? Now in a small hand, right, you could have a transistor, right, or a set of transistors in the hand, right? So enter the semiconductor, you could have discrete devices, transistors, diodes, all made up of semiconductors. Okay, and the invention of the integrated circuit was done by Jack Kilby and Robert Noisy. Jack Kilby was from TI, Robert Noisy was from Intel. Jack Kilby got the Nobel Prize for the invention of semiconductors. And most notably, right, if you are a newcomer into this engineering world and are learning, one thing very notably about Jack Kilby was the way he used to write the notes, right? So in his notebooks, he has actually written the dates when he has thought about the integrated circuit and when he actually implemented it in 1 December, month, right? And that has led him to be the got him the patent because he has written down notes with dates and been very meticulous in doing the same. So that is one notable point, right? Which typically, right, including myself, we as engineers, we missed on writing notes and documentation, right? So documentation helps a lot, and it helped Jack Kilby in getting a Nobel Prize. Okay, so 1960s, right? You see from 1950s to 1960s, right? What was discrete devices, what were transistors, what were diodes, right? use a laser pointer. What were discrete devices, transistors, diodes, or a collection of transistors and diodes? Now they have seen large scale integration. Okay, so a large collection of transistors and diodes, right, used to create gates and analog devices and digital devices, so much so that you could have a radio or a television, or the advent of the calculators, right, the digital calculators come into the picture. Okay, so that is what you see, right, and this is what we say, right, 1960s onwards is the era of the Moore's law, where every 2 years, right, we have consistently seen that the transistor count doubles every 2 years. Okay, and having worked at Intel, right, what I can definitely say is it is a self-fulfilling prophecy. For the past 50 years, right, the people at Intel, okay, they believe that it can be done, and then they do it, and because they do it, they believe that it can further be done, right, and that cycle continues, right. So that is what the beauty of it is. It's not just about the Moore's law, but it is the belief which is making things possible in the Intel world, right. So that is something to learn. So I say it's something to learn from Jack Kilby and something to learn from Intel in the process, right. Okay. So the 1970s, okay, Intel came up with the processor, their first processor 4004, and then every year or 8 months or 9 months they have been churning out new processors, right. And as soon as there is an entry of the processor, what we find, okay, there is also an introduction of software which runs on the processor. Okay, as soon as you say introduction of software, so then there is a introduction of memories. So memories where you can store programs and executables. Now those memories can be ROM memories, they can be RAM memory. Okay, so you see that after enter the processor, right? Okay, there are basically various branches that we can see. The semiconductor track taking one memory branch, the processor branch, and many other branches, right? The software branch, right? And each of these branches, right, have their own evolutionary things that have happened. Okay, but what we will be doing is we will be focusing more on the FPGA part of it and things like that, right? Then comes, right, 1980s, where not only the processor companies, okay, there were multiple processor companies. I think Motorola, Zilog, Intel, and maybe a few more, Fairchild, maybe a few more companies, right? Sun Microsystems. They started with the processor design and the whole system. IBM, they started with all the IBM 80, PCE, and so on, right? 1980s, right, what was an era of application specific devices. Okay, where you have an application in mind, say you have an application of some video processing, or you have an application of some kind of a graphics, some application where you want to run some very specific algorithm, say an algorithm of an elevator or algorithm of a traffic light, or different types of algorithms you would like to run which are useful, or an algorithm to of a vending machine, right? The algorithm of a a slot machine which is used to create what is that something in the Las Vegas, they use these slot machines for gaming and all, right? So those are some custom application specific devices, custom logic. So if there are two processors and a memory, you create a logic around them so that they can work together. You create a processor and a small subsystem around it using a printed circuit board, right, and wire wrapped PCBs, right, to create things like motor control, create things like light dimmer control, fan control. So industrial uses also started coming up in a larger way. PID control, right? Once the processor started having a lot more processing power, right? the PID control, right, started coming into the picture, and then it started using the processors and the application-specific devices also entered the area of where only pneumatic devices were used in the chemical industry, right? So it started becoming more and more popular all around. Okay, and 1990s, right, was an era or the entering, right, or you can say the beginning of an era of the field programmable devices. Now is where I will start talking about, okay, what an FPGA is, right? FPGA is field programmable gate array, right? You need not understand the meaning of gate array for now, but since we have used the word field programmable here, okay, I think that it would be good to spend some time on what is the concept of a field programming, right? So field programmable means, say for example, in the lab, right? You want to test a certain logic, okay, and you want to create an application out of it. So you create the logic, you create the application, you put it into some kind of a chip, okay. Once you put that logic into your chip, the chip behaves like the logic that you have defined. Okay. So as such, the field programmable device is nothing, but as soon as you program a bit file or something into it, right? Okay, you find that that particular chip now start behaving like the logic that you have designed. Okay, and why it is field programmable? Because sometimes you can program a FSM for a traffic light. Sometimes you can program the FSM to add 10 numbers. Sometimes you can program an FSM to like to use it like an elevator and test it out. Okay, so that is what makes it field programmable. So in the field you can program it, or in the lab you can program it, right? So enter the field programmable devices. So much so that your product itself can contain these chips, right? And these are field programmable. It's an application specific, but it's field programmable. Okay, so that is how the era of the field programmable devices came about. Okay, so from the 1990s onwards, you can say that the era of FPGAs had started. Okay, and you will slowly find, right, it is a conglomeration, right, of a processor, an application specific device, custom logic, introduction of software. All those technologies which were available till that point in time were all getting used to create a field programmable device. Okay, so it's not like something out of the blue, right? It is something that is gradually evolved, but it is going to use all the good things that were used, for other semiconductor applications. So let's go to the next one, towards the modern FPGAs, right? Okay, so we start with the ROM memory, right? So we talked about the era or the beginning of the FPGA era, okay? And then now we are talking about ROM memories. But then ROM is as old as the semiconductor technology itself. Okay. And then what is ROM? ROM is a combinatorial logic gate which can be joined, right, manually to map a n-bit address, right, an n-bit address input onto arbitrary values of m-bit data. So what a typical ROM looks like? Typical ROM, like, think of it as, I'm just trying to draw a box here. Okay, so you have an address A. Okay. So in this diagram, I have said it's an n-bit address. Okay, and you have an output Q. Okay, and the output Q, right, is m bits. Okay, so it is n bits here and m bits here. So this is your ROM, right? So this is a typical ROM. Okay, I am not even talking about chip enable and clocking and all. These are basics, just because I'm just still talking about basic using only combinatorial logic. Okay, so you have a ROM like this here, right? So let me do that. Basically. Okay, then you get the concept of from the ROM memories evolved the concept of not a concept, evolved a UV erasable programmable ROM. where what we used to do is there is this UV-Prom, okay, put it into a box and then switch on a UV light. So that chip had a glass what do you call, a glass on top of it, so that the UV light can enter the chip, and it used to erase the ROM portion of the device. Okay, and after having erased the ROM portion of the device in some 20 to 30 minutes, right, we used to put it onto a programmer and used to electrically reprogram the ROM. So that used to be called as EEPROM, or UV erasable programmable ROM. Okay. So ideally, ROM is called as a read-only memory. Okay, and then there also you have a programmable read-only memory, or a one-time programmable read-only memory, or a fused read-only memory. So many flavors in that. So we are talking about UV erasable programmable. Okay. Next, right, as a evolution came in electrically erasable programmable ROM. So now you don't need the UV light anymore. You can put it onto a programmer. You can give a high voltage to it to program it and even erase it. Right. So you can electrically erase and you can reprogram the ROM. So you can see here, right, if this ROM image, if I'm able to reprogram it, okay, from time to time, okay, then I can change. So if there is a program to add 10 numbers, I can reprogram my executable into the ROM and make the processor to run like run a function of adding 10 numbers. Right. If I want to, if I write a program for doing some kind of a algorithm, right, which will multiply two numbers, right, using subsequent additions and left shifts and right shifts and all, right, that is something, that algorithm I can put it as an executable into the ROM and make the processor execute, right. So that was the beautiful use of using the programmable ROM, because it is programmable. You can use the same ROM for multiple applications. Okay. Then came the the next step in the evolution, right, called as a programmable array logic. So somebody looked at the ROM related design, and they said, hey, you know what? I can use this ROM related design for something else. Okay. And what was that something else? That something else is programmable array logic. Because anyway, there is a combinatorial logic gates in this ROM. Okay. And can I not make it programmable? Anyway, you are able to program a programmable ROM by electrically erasing it. Can I not, use this same concept as a programmable array? Okay. So the way to do it was consisting of two main components, right? Now I can break it up into hardware component and a software component. The hardware component again can be broken up into two parts, right? One was a logic plane, okay, which consists of logic cells, right? Like the Boolean cells, like AND or invert. So this AOI means AND or invert. Okay. OAI is OR and invert. IAO is invert and OR, right? It's like different ways of, you remember, right? We used to do Karnaugh map, right? In which we used to say, okay, this is a sum of products method and product of sums method. So same way, right? You have AND or invert, OR and invert. But all in all, it is a way to implement a Boolean function, right? So you have a Boolean function, and associated with it is an output macro cells. So two main components, hardware and software. Hardware also two components. One is a logic plane and other is a output macro cells, right? And in the software also, right, you started having two things, right? One is a software itself, like a PAL ASM or a PAL assembler, okay, which can take in a Boolean expression in a text format, okay, and then it will create a fuse map file which can be programmed into the programmable array. And the differences in the fuse map file, right, will tell you what application is being run. Okay, so that is the evolutionary stage, right, that has happened. So what we have done here, right, is just to give you a sneak, like a peek, right, into what was there and you will see that these are scanned copies from a very old textbook kind of or a very old book from monolithic memories, right? And this is a handbook from monolithic memories, right? So figure, right? So there used to be an AND gate, and that AND gate, right, is represented like this, right? Wherever there is a cross, right? Okay, that one is taken, right? So you have a cross means that there is a A, B, and C. Okay, so here, right, if you see here, you have crosses all over, and you have a I1 and I2 two inputs. You can have a inverted version of it and a non-inverted version of it. Okay, so I2 also you can have a non-inverted version of it and an inverted version of it. So if you see, right, wherever you have a cross, okay, so here if you see, yeah, okay, so wherever you have a cross, right, okay, or not a cross, right, you will get the feeling of whether it is the AND logic is there or it is not. Okay, for example, right, take an example PAL logic, right, where you have an output expectation which is I1 into I2 bar. So I1 AND of I2 bar plus I1 bar AND of I2. So it is this logic, right? So you have two AND gates followed by one OR gate. So here also you have an AND or invert. Okay. So here you see, right? You have an I1. Okay. So you have an I1. So you have a cross here at I1. Okay. And you have another cross here, which is a I2 bar. Okay. Let me see if I can show it in terms of a pen. So you have a pen. Okay. So you have a I1. Think of this I1 is going to an AND gate. Okay, so this is I1, and then you have an I2 bar, right, going as an AND gate. So here you saw two crosses, right? So it means that this term, right, is I1 into I2 bar. So this is that term, I1 into I2 bar, this term. Okay, and what is this other term? I wish I can change the color. I can change it. Very good. Okay, so what is this term? If you now it becomes very evident to you, right? So this term is I1 bar, the blue colored one, okay, into I2, right? So this term, right, the second term, okay, is this. Okay, so now using this itself, right, now we are able to create a logic, okay, using a invert. So this is a invert part of it. Okay, this is the array part of it. Okay, this is the AND part of it, and this is the OR part of it. Okay, invert array. So this becomes like a programmable logic. Okay, and the technology at that point in time allowed you to put these gates. Okay, so now, right, what we are trying to do is again take some some steps forward, one step backward, right? You'll see, right, what earlier was a PROM and a PAL PLA, right? So I said, right, somebody had a good idea. Somebody who was designing a ROM, right, had a good idea. In the ROM, what they used to do, okay, you have an address, right? Say, for example, this is a 16 words into 4 bits ROM. Okay, so if you see this is a 0, 0, 0, 0. And this whole output, right, could be any one of these OR gates, right? Whatever you program here, right, as a 1, 0, 1, 0 would come out as a output on the O0, O1, O2, O3. This used to become 0, 0, 0, 0, 1. Similarly, right, if you start seeing, right, this is 1, 0, 0, 0, and like culminating in 1, 1, 1, 1, which is ROM, right? These are all the 16 inputs, right, of the 4 bits, right? 4 bits means it will convert into 16 inputs, or 4 inputs. Okay, you could have 16, in the 2 to the power 4, right, will be 16. So you will have 4 outputs here. Okay, so now this acts like a ROM. Now somebody is thinking, right, what if I just go and populate all of these and allow everything to be programmable? So that is what they have done here. all of this, right? Even on the left hand side of the array and the right hand side of the array, right? Of the invert and or, okay, is also programmable. Okay, and that gave word to PLA, programmable logic array. Some people call it as a, PAL, or programmable array logic, right? So either you call it as a programmable array logic or programmable logic array, right? It means the same thing. It's just how people use the word. Okay. Next is, right, if you see that typical logic gates or typical FSM, right, require us to have a feedback of inputs, right? So whatever you have given output, right, you want it to be feedback as inputs. Okay, so what happens is the high-end members of the PAL family, right, will have a programmable input and output. Okay, the output is also fed back into the PAL array as input. Let me put it here. Highlighted. The output is also fed back into the PAL array as an input. So this is what is happening here. Output is also fed back as a PAL array. Okay, and if you see here, right, in the IO, okay, you are having an output enable also. Okay, so this OE is an output enable. Okay, so you have another term, okay, another AND or invert type of array, right, which will go and attach itself to the OE of an IO, output enable of an IO, and there is a input feedback, right? So you are taking an input feedback from there. Okay, so these are all the things that will enable a user, right, to create his or her own, logic circuit. Okay, and yeah, this is a typical FSM, right? You have a state machine, the Mealy type state machine, where you have inputs and memories or the state, right, which is determining the output logic and the outputs. Okay, and pure Moore machine, right, will only have the the memory and output logic coming in. The memory is the states of the state machine. Okay, so here what happens, we can be able to map a generic FSM. That is the intent, right? We should be able to map a generic FSM onto a PAL, CPLD or FPGA. Then a lot of applications can get fulfilled. Okay, data entry can be in the form of a Boolean equation or a schematic entry or a Verilog VHDL RTL. Correct. So all these, this is the order in which I have written it here, right, is also the order in which the evolution has happened. We started with a PAL ASM where only Boolean equations are there. Then you have combined multiple Boolean equations, got their outputs, and using schematic entry connected them. Then you said, okay, connecting so many wires and all is becoming difficult. Writing so many Boolean equations is becoming difficult. We want to write it in a higher level of language, or go to a higher abstraction level so that we can achieve more things, right? So VHDL and Verilog came into the picture, right, for the RTL. Okay. And the last one, right, which I would not have mentioned earlier. So we talked about combinatorial logic till now, right? Okay. But here, right, we see the advent of, or we see an evolutionary sign, right, where you have registered outputs also, and the feedback is also there. So you see this Q bar, right, goes in as a feedback. Okay, so you have a flip-flop. So this, right, by doing this, we are able to achieve, right, IO. We are able to get kind of a registered or a memory element, and you have Boolean logic all together. So a FSM can be peacefully created out of it. Now, what may be the limiting factor is, okay, how many inputs the FSM should have, how many states of the FSM should be there, and does the PAL, right, actually have that many flip-flops or not? Correct. So except for those limitations, right, we are able to see that a lot of FSMs can be created. And if FSMs can be created, a lot of small designs can be created and made to work. Okay. Back to main project. Okay, so we were at PALs, right? Okay. So from the PALs came the concept of a CPLD. Now you see that from the PAL, right? Now every 2 years you are seeing the Moore's law is still working, right? Okay, so you can integrate more things into the device. Now if you already have a PAL device, okay, with that AND or invert or AND kind of an array, right? Can you not just replicate all of these arrays and say that, okay, I'll have an array of these PALs, okay? It means that I can have more bigger FSMs which I can put, or I can have 2 or 3 different FSMs can be put on the same chip, and they can interact with each other and do a lot of input output activities, right? So, and along with that, right, you also have PAL ASM, right? Okay, and now it has to start accepting preliminary construct for hardware description language. HDL is hardware description language. Okay, so that is what we are seeing as a, from an evolutionary trend, right? So here you see, right, this is a macro cell from a MAX 7000 device from Altera. Okay, so you have all these product term select matrix, which was there in the original PAL, right? Now you have product term select matrix and parallel logic expanders, which are coming from the other macro cells. And then from the same macro cells, you are also seeing that there is a feedback path. Not only that, you are having an OR array followed by an XOR. Like XOR is almost like you are adding more gates to it. You have an invert output, which is going to the clear, right, of a programmable register, PRM, or programmable register programming. You also have a bypass register to control the IO block, right? And it goes to shared logic expanders, global clocks, global clears, clock enable select, okay? And the final output, right, can go to a PI or programmable interconnect array. Even the interconnect, right? Now you start seeing that the interconnects are also becoming programmable. So you see that there is a programmable interconnect array also. And this whole thing, right, is a small macro cell in a bigger PAL, right? So let's go to the next foil. This is a small macro cell. Okay, so like this, right? What this is again the MAX 7000 architecture. So you see, right, the numbering, right? 32 means it will have 32 macro cells. 64 means it will have 64. 96 means I will have 96. So you have that family of chips, right? The concept of having a family of chips, right? And the family of these chips, okay, you have a macro cell which in turn has a kind of a PAL array, okay? 1 to 16, 17 to 32, 33 to 48, 49 to 64. So you have, and they call it as a lab, logic array blocks. A collection of PALs is called as a lab in this case, right? Okay, and you have a macro cell. So this is combined into a macro cell. You have expander product terms. You have a programmable interconnect array, which is this one. So all the inputs and outputs coming from the macro cell or going to the macro cell, right? Okay, or coming from the IO block and going to the IO block are connected here through the programmable interconnect. Okay, and you have these IO control blocks itself. Okay, so slowly, what we are seeing is that as the technology evolves, as the Moore's law is evolving, what started as a PAL, right? Now you are having a collection of PALs, and now you are calling it as a CPLD, right? A complex programmable logic device. So that was the concept of a evolution where CPLDs came into it. Nowadays CPLDs are even more complex than what I've just showed you. Okay, but that is how it is, right? So Moore's law continuing, and we still talking about Moore or more than Moore, right? So next, right, as an evolution from CPLDs came the FPGAs or the field programmable gate array. Okay, so here we saw CPLDs, right? There was a collection of PALs, but in FPGAs you see me using a different word, collection of configurable logic blocks. Now, what are these configurable logic blocks? We will come to it slightly later. Okay, it also has programmable interconnects, programmable IOs. Okay, and the software, right, has gone from economy class to business class, right? you are now started taking HDL as an input design entry. So you can still do Boolean equation, you can still do schematic entry, okay? But predominantly for FPGAs, right, the system designers have started using HDL or like VHDL or Verilog, right, hardware description languages, as the main method to give an input design entry. Okay, and the tool is going to take this input design entry, do a synthesis, mapping it onto the field programmable gate array, okay, and creating a bit file. That bit file is what earlier we used to call as a programming of the ROM, right? So think of it in that direction, right? So if you look at all of these, right, this is the idea that comes into somebody's mind, right? If you are the very initial designer of the FPGA, you will say, okay, I am doing my first FPGA, so I will create a FPGA like this, right? Where you have an array of CLBs, an array of IOs, and this the purple colored ones are the programmable interconnect arrays. So basically 3 blocks, right, consist of your FPGA. Now we are still evolving, right? So PAL to CPLD to FPGA. And in FPGAs also now we will start seeing how the evolution has gone further. Okay. So basically, right, I've come up to the basics of the FPGA and I've stopped and said, okay, this is the time, right? We would like to take a few what you call observations. Okay, what are the first observation? The first observation is FPGA or a CPLD is an already hardened property. It means that gates are already present in the design and in the chip. Okay, so whatever is our RTL as a system designer, right, or our design, or our FPGA, or our Boolean logic, or our FSM, right, has to be mapped to whatever was in the device. Okay, so it means that the device had 10 flip-flops, and if I only use 8, the device will still have 10 flip-flops, but 8 of those flip-flops will be used for the design that I have created. Right? Other 2 flip-flops remain unused. Their outputs remain unused. Okay, so the RTL must get mapped into whatever is there in the design. Compare that with an ASIC. If I am having an RTL with 8 flip-flops, okay, only 8 flip-flops are going to get implemented, right? So ASICs is much more flexible, right? It means it will be more exact to what you are doing, right? And the synthesis and physical design flow determines the gates and layout. Okay, so you can determine, right, what kind of gates you want. You want a high drive strength gate, or you want a lower drive strength gate, or you want a particular, instead of having 2 AND gates followed by an inverter, you could have an AOI gate, or many such muxes. You could have many such, combinations and permutations that you can use to reduce your gate count and improve your timing and, reduce the area of the layout and the chip itself. Right? So you have much more flexibility as a user to control what you want. Okay. So that was one observation in this. Okay. What is the second observation that we had? Okay. For an FPGA, the bit file determines the functionality of the device. If I program a bit file which does only traffic light control, it will work as a traffic light control. If I program my device, right, to work as a PWM or a pulse width modulator, right, to control a fan or some kind of a motor, it works as a motor control, right? So the bit file determines the functionality of the device. Whereas for processors, what happens? Whatever we write as a software determines the functions that are to be run. If I write a function in software to add 10 numbers, it's going to add 10 numbers. If I write an algorithm in software to do some kind of a complex integration or derivative, right, like a sine, cos, theta, and all those kind of things, right, Taylor series and all, right, then it runs the function that I need to run. Okay, so the software executable determines the function to be run, whereas in FPGA, the bit file determines the functionality of the device. Okay, what is the third observability? The third observability is FPGAs can be EEPROM based for fixed functionality. Okay, And for development purposes, the FPGA can be used based on static RAM. So it means that if I have a static RAM, instead of fuses or bit file programming from EEPROM, right? I can go and program that static RAM to whatever bit file I want and create numerous numbers of designs throughout the day, debug them, and once it is made, stable, then I can say that okay, let me go to a smaller device which has an EEPROM and make it a fixed functionality for final production. Right, so that is the third observation. So that EEPROM concept is not going to run away. Okay, but for additional functionality, a static RAM based FPGA start getting created. It means that wherever we thought that we need a EEPROM bit in place, a static RAM bit is getting put in place. Okay, and the concept was that in a large scale integration, 6 additional transistors for a static RAM, okay, is not a big cost because it gives you a lot of flexibility in terms of regroupment. Okay, so that is the justification that is given for allowing a static RAM based FPGA. Okay, what is the fourth observation? And see, it's a very key observation, right? That FPGAs can keep pace with shrinking technology. Okay, so yesterday I had a 125 nanometer design. Okay, that became a 90 nanometer, 45 nanometer, 28 nanometer, 16 nanometer. Okay, and further, right, 10 nanometer, 7, 3, whatever, so many angstroms, right? So whenever we are seeing the the improvements in the technology and shrinking of the sizes, right? FPGAs can inherently keep pace with the shrinking technology dimension. Why it can keep pace? I mean, at least in our thought process, right? We can say that okay, if I am able to design one block and I just multiply that block in an array format, right? I will be able to place my design in the layout, right? So what happens is every time, right? FPGAs can always keep pace with the shrinking technology. Whereas for other technologies, say you are creating an ASIC for MPEG-4 design, right? Okay, and if there is a shrinking technology, you either write it into a RTL and get it synthesized, or if you are doing, some tailor-made, handcrafted custom logic, right? You have to redo the custom logic for the newer technology node, right? So migration from one technology node to a better technology node, right, becomes easier in an FPGA, at least in our thought process, right? And so FPGAs can keep pace with the shrinking technology dimension. So these are 4 key, according to me, right? These are 4 key observations, right, on the FPGAs too. Okay, now let's go to the economics part of it. Okay, so all of this we do technology things, right? But if the economics fails us, right, it typically doesn't get materialized, right? So what was the economics part of it? Let's go and see, right? The ASIC and SOCs, right? So now is the time when I should express what is an ASIC. ASIC is a application specific integrated circuit. And what is an SOC? SOC is a system on chip. Okay, so and say an MPEG decoder could be an ASIC. Okay, but a processor combined with some analog to digital converter or a D2A converter and some kind of a filtering logic built into it is a system on chip. Okay, so have that difference what an ASIC or an SOC could be. And these lines, right, they typically blur as the integration happens very highly, right? So with very high integration, some of these lines get blurred. Okay. And processors were typically designed and hardened to cater to markets with large volume. Right. So if you have a large volume, you can go all out hardening. You can do a lot of things to squeeze the last millimeter out of the design that you have. Right. So for large volumes, processors, SoCs, ASICs, which are good. Okay. So creating your own chip. But what about designs which do not have a large volume? Do they have to go through all the 9 yards for taping out a chip? Just because you had a few thousand parts, right, to be sold, or a few thousand products to be sold. Okay, so that was what happens to those kind of design. We do not have large volume. Okay. Then the question is, would it make sense, right? You have one device which can be produced in large volume, okay, but it can be used in many places in applications which run in low volume, right? So if a large processor like the Intel kind of devices are going ubiquitous in all the PCs, right? Okay, but what if there are applications, right? You have one FPGA, okay, and that FPGA 100,000 get used in aerospace, 100,000 gets used in traffic lights, other 100,000 get used in some other application. Okay, some things are used in cars, some things are used in washing machines, some things are used in microwave ovens, some things are used in fridges, right? And so on, right? So what happens, right? Does it make sense? People are asking that question. But you have one device which can be produced in large volume, but it is used in applications which are running in low volume. Okay. Would it help amortize the cost of production of the device? With risk, answer is yes. Okay. So, does the PAL, CPLD, FPGAs make sense from an economics? And I think I spilled the beans, right, by saying the answer is yes. Right. So, as soon as somebody finds that the answer is yes, what are they going to do? Right. You go build a versatile device. Now, this is the very key word here, right? Build a versatile device, okay, which allows the users to define the application. Okay, a versatile device which allows the user to define the application. Okay, and then what you do, you incorporate tremendous flexibility in the device to cater to multiple markets. You give so much flexibility, right? That any market you want to, target, can an FPGA do that job? If the answer is yes, go ahead and pick up an FPGA and start using it. Okay, so that is the funda. You incorporate tremendous flexibility in the device to cater to multiple. Okay, so incorporate tremendous flexibility. Okay, now let's see the uses of the CPLDs and the FPGAs. Okay, what are the uses of CPLDs and FPGAs? There is a one single answer to it: ubiquitous. It is used everywhere. Okay, so let's name a few, right? And whatever I name, right, you will always find that there will be an application which I have not mentioned here, but it is used there. Okay, so basic gates, there will be glue logic, decoders, MUX, registers, FSM, GPS. So this is that era of the PAL and the CPLD, right? Still into the large scale CPLDs, right? Automotive and aerospace, engine control, in-car entertainment, FPGAs are used, ADAS, CPLDs, auto communications, FPGAs and CPLDs, right? They are getting used. Medical application. See, medical applications are not, I mean, you don't find, CT scanner, CT scan machine everywhere, right? It's not ubiquitous. But wherever it is, you need some chip which will do imaging, right? FPGAs are well suited for that, right? So for imaging, monitoring sensor, scopes, endoscopy, bronchoscopy, scopes, right? MRI, CT scan, right? So it's used in medical application. Audio and video processing, MPEG encode, MPEG decode, filtering, rendering, security cameras, right? And the dot means that there might be many more which I may not have even written down. It's like saying etc., right? Okay, I/O communications, USB, PCI, like you have the mouse and all, right? SPI, UART, I2C, SerDes, LIN and CAN, right? Used in the automotive, Ethernet, and JESD. There could be many I/O communication methods, right? Okay, digital signal processing, neural network processing. Okay, so these are the places, right, where you find, the usage coming into the picture. One second, I'm trying to. Okay, so Yeah, I think the machine went slow. So this was digital signal processing, neural network processing. Okay. Then next is in chip design itself. Okay, so people use FPGAs to do chip design, ASIC design, SoC design, right? And even processor design, right? So they used as a hardware assisted verification. So if you are designing a new processor, can I put the new processor into an FPGA and check whether parts of my processor are working okay or not, right? As in hardware assisted verification or emulation, right? Emulation means, can I use an array of FPGAs, okay, and put my complete design into that FPGA and make it work? For example, the Sun Microsystem, right, used an array of FPGAs at 500 kilohertz and booted, Sun Solaris on it even before the tape out of the chip, right? So that is the advantage they get. So chip design, hardware assisted verification or emulation, right? Can I use an FPGA tile as an IP in a larger SoC, right? So we say, right, a system on chip could have a processor or a set of processors and a large set of peripherals and intellectual properties like a DMA, a DDR memory controller, PCIe, USB, SPI, I2C, and many more, right? Can FPGA be used as a IP tile, which is a programmable intellectual property, right, in a larger SoC, right? It is possible. Okay, it's used also in robotics, space, machine tools, and manufacturing plants, right? So it is used, say, in a distillation column. It is used in a boiler, right, and so on, right? Power generation, power distribution, farming, right? So you see these what you call drones, right, with cameras. They go in the farm and they take photographs of the plants and they figure out that, okay, this particular location, right, has not been receiving enough water, right? So they go and sprinkle more water in that area, right? Just based on the color of the leaf and all that, right? They're able to do it. So that's how farming is using these CPLDs, FPGA. Military, definitely. Space, shipping, right? FPGAs can also be used as substitutes for ASICs that have become end of life or no longer in production, right? So say, for example, Intel does not produce an 8085 anymore, right? But if in your BTech program you want to learn an 8085, what do you do? Okay, so nowadays, you could have an FPGA and then you could have an RTL for FPGA. You can burn that FPGA and okay, now your teacher can teach you 8085, right? As a beginner's way of teaching computer architecture. Okay, used in data centers, right? So you see, right, effectively the uses of PALs, CPLDs, and FPGAs. There is one word to it: ubiquitous, right? And whatever we would have written down here is just a tip of the iceberg. There could be really many more applications which I may not be aware of, but that's how it is, right? It's based on my limited experience. Okay. So next one, right? After the uses of the CPLDs and FPGAs, okay, what is the development cost versus time between FPGAs and ASICs? Okay. So we only have one file for that, and maybe it looks like a marketing file, okay, where we say that, okay, programmable logic, within days you will get it work. Whereas if you have a gate array, it takes months, right? So field programmable gate arrays maybe in months, but if you are doing ASICs and full custom design, maybe it takes many more months and years to do, right? So as you see, right, this up to here, right, the gate array. Okay, so up to here, right, if you see, right, you find that, so let me put this as FP. So it's a field programmable gate array. Okay, so in gate arrays, right, you can get up to months, right, you can get it, but in standard cells and full custom, right. So this is the FPGA world, this is the ASIC and SoC world. So this is the development cost. right? So that is how it works. Okay. Next, so you see, right? These three topics, right? The economics part, the uses and development. I would have gone a little bit faster, but let's delve little more into the concept of a configurable logic gate and the FPGA block. You would already have seen the basic FPGA block diagram, which consists of three things, right? What are the three things? One is a configurable logic block itself. Okay. The second is a programmable interconnect, and the third is the IO. Okay, so let's go to the. Okay, so you would have seen the CLB, which is the pink colored one. Okay, the programmable interconnect, the purple colored one, and the gray colored one is the IO. Okay, but what happens inside? Now let's zoom inside a little bit, right? Now what happens inside? What is a CLB, right? Think of a CLB as a mux and a flip flop as a basic building block for the FPGA. Right, so you have a 4-input LUT. Now you see me talking about LUTs once again, right? Like we talked about ROM, right? We are now again start talking about an LUT, which is it's like a ROM, right? And you have a flip flop, okay? And this CLB, right, or a configurable, I said it is an easy CLB because it's like a very trivial. But even though it is a very trivial, you can actually implement any logic with this or a combination of this CLB. Okay, if you have easy CLB or an array of easy CLBs with a good decent programmable interconnect, you can actually implement any logic model. Okay, so you have a 4-input LUT, which is say a combinatorial part. The output of it goes to a flip flop, and the output of the flip flop input to the flip flop, output of the flip flop, we call it as a QZ because it is a registered output. And then there will be a combinatorial output directly tapped from the output of the 4-input LUT, which I have called it as Z. Okay, and definitely a flop will have a clock and a reset associated with it. So we said, okay, we will go into the wiring of these lines also. Okay, now you see these two RTL, right? You have a module called Boolean equation, and there is an input A, B, C, and D, and the output is Y or Y. And there is an assign statement, right? It's a combinatorial assign statement, Y is equal to A and of B plus C and of D. And in the other, the yellow colored box, right? So the gray colored box is a combinatorial logic, pure combinatorial logic. Okay. And the yellow colored box where I have put always at passage of clock. So it looks like a sequential output, right? So Y is assigned to A and B plus C and D. Okay, A and B plus C and D, right, is a combinatorial part. But Y getting assigned to this combinatorial part makes it a sequential cell. So here is a pure combinatorial part, and it's a combinatorial plus sequential. Okay, so now you think, right, in your mind, try to map the below RTL modules to the easy CLB. These two RTL modules, right, you try to map it to this particular easy CLB. How does one do that? Okay, what would happen in an ASIC, right? In an ASIC, okay, the first one will actually become two numbers of AND gates. One AND gate which does A and of B, right? So one AND gate which will do A and of B, another AND gate which does C and of D, and the third OR gate, right? Okay, OR gate which will do A and of B plus C and of D, right? Okay, and here in this case, in the second case, there will be what you call a sequential cell, or the output of the AND and OR will go to a sequential cell. Let's go to the next point to explain this. So the same thing is there in this point, right? The mux and the flip-flop is used as a basic building block. Okay. In an ASIC, right, you will see something like this. In an ASIC world, right, you will see some two AND gates followed by an OR gate, and you are saying a Y is equal to A plus B, A into B plus C into D, and then you could have a flip-flop based on whether it's a gray colored combinatorial logic or a yellow colored combinatorial plus sequential. So what we said, right, in the previous foil is the mux and flip-flop, right, act like a basic building block for an FPGA or the CPLD. And the same two Verilog pieces of code, right, the gray one, which depicts only a combinatorial logic, and the what do you call it, the orange or the ochre colored one, right, which depicts a combinatorial and a sequential cell, or as or a flip flop getting added. Okay, if that logic, right, y is equal to a end of b plus c end of d, right, were to be done in an ASIC, right, it would look like this. This would be a ASIC implementation, right, of the combinatorial logic. Okay, and in front of it, if it was flip flop was there, then we would say that okay, I'll put a flip flop in front of it. Okay, you have a D here and a Q here with a clock and a reset and all that, right? So this would be your new Y. So that would have been the case if it was a ASIC, right? Now what happens is, in a lookup table based methodology, right? There is a Boolean equation. You create A, B, C, D, and the Y as a table. Okay, and now you have 16 methods in which 16 ways in which A, B, C, and D can be put. Right, and based on what the Boolean equation is, right? If you would have seen, if C is equal to 1 and D is equal to 1, Y will be 1. If A, B, C, and D all are 1, then again Y will be 1, and so on, right? So in the dark green color, right, we have tried to highlight, right, all the combinations that will make the Y is equal to 1. And the same thing, right, we have put it as a table here as an input to the mux. And what is that mux? The mux is a 16:1 mux. Why did we put 16:1? Because we have a 4 input LUT. So you will have 4 select lines, okay, S0, S1, S2, and S3. And each of these select lines will, you can map it to A, B, C, and D, which are the input signals of the LUT. And this is where you give the stimulus to the LUT and design, right? So for example, if my A, B, C, and D, right, was 1, 1, 1, 1, right, then this number 15, right, this row will get used, and you will get an output of 1. But if it was 0, 0, 0, 0, right, then the 0th row will get used and the output will be 0, and so on for each of these 1s and 0s, right? So that is how A, B, C, and D's acts like an input signal to a 16:1 mux. Now what happens is the output of this LUT can either go to a flip-flop, okay, if it was a sequential cell, or it could go to a 2:1 mux, which will decide, okay, whether the sequential output will go or the combinatorial output. Okay, and each of this, which we have marked it in the light green color, become a static RAM of the LUT, right? So the mux input is a static RAM, right? For example, if it is 1 if sequential cell is used, and 0 if combinatorial logic is used. So this is that yellow colored logic and blue colored path, right? So yellow colored path and the blue colored path. So you see these arrows, right, will depict what the path is getting taken. Okay, so this becomes like a configurable logic gate, right, which is a basic building block of a FPGA. Now, I mean, having said that, right, I'm sure that real designs will be not as trivial as this. Real designs will be more complex than the way it has been showed here for illustration. Okay. So after configurable logic blocks, what's the next thing? The next thing is the programmable interconnect. Okay. How do you do a programmable interconnect? You create wires horizontally, you create wires vertically, and wherever they join each other, or wherever there is a wherever there is a junction, right? Okay, you have an array of muxes. So for example, right, the junction here will have 3 inputs because the 4th one is itself, right? And the output of it, right? And you see that it's like an IO only. So there is an output enable kind of a thing, right? So you have a mux with 2 inputs, right? Because it has to select one of 3, right? So you could have some kind of a, each junction having a array of muxes. And each of these mux ka outputs, right, mux ka select lines, right, could be one of your static bits of your bit file, right? So think of it that way, right? So this is how a interconnection between configurable logic blocks is done. You may have noticed that I'm still not talking about the IOs, right, of the uh, of the FPGAs yet. We'll come to it. Okay, so this was the concept of configurable logic and the FPGA block diagram. Okay, next is we'll go into different flavors of FPGAs. What are the different flavors of FPGAs? Okay, as soon as we say that I have a CLB, right? Everybody thinks differently. They could have a size of the LUT could be 4 or 6 or 8 or even more, right? You could have configurable 8-input LUT which can be split up, right, based on the application as 2 numbers of 4-input LUT. You could have additional muxes, additional XOR gates, additional shift carry logic, additional flip-flop, right? And hence, right, there could be very many different types of CLBs that can be created. Different companies create a CLB in a different way, right, based on the innovation that they are doing in the Boolean world, right? What there could be a differences in types of interconnection between CLBs. Okay, so all the purple colored ones, right, the interconnects between CLBs. There could be a special network for clocking, right? So clock routing within the FPGAs, right, with multiple clocks going as inputs is also a very complex matter, right? So clock routes are dedicated within the FPGA because they need to maintain low latency. If there are multiple clocks going on to a clock tree, then there should be a clock mux to enable the selected clock on the route. So that's why I put quotes, right? The selected clock is the clock that we have selected as part of our application. And these are dedicated routes designed for low latency. Okay. And optionally, you can use it for high fan-out nets that can route on the clock network by using Pragma. What are high fan-out nets? Clocks are one high fan-out net, which means low latency. The other high fan-out nets are resets. Sometimes you would have test enable signals, right, or scan enable signals, right? Or many other enable signals, right, which need to be on a very high fan-out because they are going to enable or disable pieces of logic, right? And that piece of logic will have a enable there as a min term in all their gates, right? So you have a dedicated clock routing within the FPGA, right, as a part of the interconnect. So interconnects for high fan-out we discussed, right, like resets. You could have a innovation, right, like an hyperflex register, where the interconnects itself are having registers to enable the pipelining and timing closure. Okay, so think of it. So this is a hyperflex register, right, from Altera. Okay, so you would have a general interconnect where you have a routing multiplexer, okay, and there could be a RAM configuration which is part of the bit file. Okay, so output of this particular mux, right, you could have a flip-flop and a further mux connected to it. Okay, so it means that if you want to meet timing, okay, you may not want to use a flip-flop which is there in your lab or a ALM, right, or what they call, and you can put it in one of the hyperflex arrays itself, right? So new hyperflex registers are throughout the core fabric. Okay, so logic is used within of the ALM and the registers are used throughout the core fabric, which will allow you to do a lot of pipelining and make your timing closure in terms of setup and hold time, right, easier to meet. Okay, so these are some evolutionary innovations, right? And sometimes they are not evolutionary; they also tend to be revolutionary, right? Innovations that happen in chip design. Okay, so you see different types of CLBs, different types of interconnection between CLBs, and there is one thing which we have not discussed yet, right? different types of IOs. Okay, you could have general purpose configurable GPIOs or general purpose IOs. Okay, you could have IOs with different voltage signaling, like 1.2 volt, 1.5 volt, 1.8 volt, 3.3 volt, 5 volt, and so on, right? Maybe in the next generation you could have a 1.8 volt also. Okay, you could have low voltage differential signaling LVDS IOs, again with different voltage ranges and their delta ranges. You could have a SerDes or a serializer and deserializer, very high speed gigabit transceivers. Right, so those are the possibilities in terms of IOs that can be held. Okay, and IOs typically are, it will be at the peripheral of the chip. Okay, here I am only considering the FPGA IOs itself, right? I am not considering, okay, how you will power your CLB, the IO that is needed to power your CLB, right? That is, we are not considering that. That comes as a part of the FPGA design itself, like when you are designing the FPGA itself, right? But from a user perspective, you will only say that, okay, these are my power rails in the design, and this is how we are. If we put this voltage on the power rail, the FPGA will work, right? So, and you could have maybe groups of IOs, some groups working on 3.3 volt, some groups of IOs working on 1.8 volt. So even in IOs, right, you could have many flavors and grouping depending on the application and the FPGA that you have chosen. Okay, not only different types of IOs and CLBs and interconnect, but even differences in count also, become a part of the GA family, right? So like you saw in the Altera, right? One is a 36 labs, another is a 64 labs, another is a 96 labs, and so on, right? LAB labs is a logic array block, right? You would have seen in the Max 7000. Okay, so not only different types, but also differences in the count, right? So here we have shown a 4x4 CLB, right? But you could have an FPGA which is a 64, right? 8x8, or a 32x8, and so on, right? Or even bigger, right? I'm just giving you the names to give the feel of how one could create a family out of the CLBs and IOs and interconnects. Okay, so now that this is over, let's get back to the agenda. Different flavors of FPGA. Okay, now let's talk about that. What are the different flavors that are coming up, at least in the rapid evolution that has happened in the current year, right? In the last 5 years, right? Addition of hardened macros within the FPGAs, okay, have become a norm, okay, for quick and ease of use, right? PLL blocks for supporting multiple clock domains. Okay, so nowadays designs have multiple clock domains, so FPGA vendors are start putting PLL blocks to support multiple clock domains. Block RAMs to support on-chip memory. Right? What are these on-chip memories used for? Used to include memory like a RAM, ROM, used for FIFO, deeper lookup tables, and so on. Hardened serial peripherals like UART, SPI, GPIO, I2C. Some people even have hardened DSP blocks, which includes multipliers, adders, ALUs. Hardened ALUs. Look at that, right? It looks so good. You see this one example, right, from an Altera block diagram of ALU. They have DSP implementations which will allow for fixed point and floating point arithmetic. Okay, so you have this array of inputs, registers in between them, a first array of multipliers, 4 multipliers, first array of adders, and the second array of adders, and then there could be a chain out adder followed by an output register. Right, and maybe there is a chain in and a chain out with a mux and so on. Right, but the purpose of all of this, right, is that if you are really interested, right, try to take this block diagram and say to yourself, okay, if I were to do a complex multiplication, like A plus IB multiplied by C plus ID, where I is root of -1, right? A complex multiplication. I'm not saying complex in terms of the literal complex. I'm saying it's a complex multiplication in terms of the mathematics of complex numbers, right? So if you try to map a complex multiplication in this particular DSP block, right, then you get the feel of it. Or you try to map complex multiplication followed by a saturation and rounding, right? Whenever some number crosses a particular limit, you have a saturation, and then you have to round a number, right? If it's 18.5, you want to make it 19, or if it's 18.25, you want to keep it as 18, right? So those are some kind of things that these blocks allow you to do. Okay. So hardened DSP blocks, security IP, right, which can do encryption and decryption on the fly, right, which is hardened. Analog components like ADC and DAC, they are now becoming part of the FPGA itself. So, for example, this whole thing is an FPGA component, right? Hardened ADC block. Okay. The only digital part connected to is the digital reconfiguration port, the DRP, a JTAG followed by a FPGA interconnect on that. So through the JTAG, right, you can configure these control registers and read the status registers and even read the ADC data and so on. So analog to digital, so you have a digital value. That digital value to be read by the FPGA interconnect. If you are debugging something, you can read it through the JTAG. Okay, so and even in this, right, being an FPGA company, okay, they will provide a lot of configurability in terms of you can have multiple external analog inputs. You could have multiple A to D converters. You can use both, or you can use only one of them. Maybe there is a programmable reference that you could give, programmable register for sample and hold. Right, so those are some features, right? As an FPGA company, they would definitely give. Okay, so you could have analog components like ADC and DAC built into it. Okay, for RF now you start seeing, right, words which are like more application specific. RF communication based component like digital down converter, digital up converter, digital pre-distortion, crest factor reduction, JESD SerDes, and so on. Right, so DDC, DUC, DPD, CFR, JESD, all like domain, very much domain specific component, but then they are hardened macros. That is the thing. So these are now start looking like a hardened macro. So this now start looking like hardened macros within of the FPGA. Okay, not only that, right? Massive monolithic integration, massive multi-chip module usage, right? Chiplet technology, stack die technology, they allow you for a new wave of FPGA, right? What is a new wave of FPGAs? It's an FPGA with a complete processor subsystem. Okay, so you can see here, right, is an FPGA. So this is from one of the I think, yeah, this is a generic, right, FPGA, right, from Altera or Xilinx, right? So they have a complete system called as a processing system. Okay, the one in the blue color, and a programmable logic, which is actually the FPGA gate array, right, as the yellow colored one here. See the amount of processing that they have given, right? The complete processing system, right, consists of 2 numbers of Cortex A53. 2 numbers of Cortex R5 real-time processing, okay, 256 kilobytes of on-chip memory with ECC, LPDDR and DDR controller, multi-channel DMA, timers, watchdog timers, resets, clocking and debug. So that through JTAG you can debug your processing system. You can put a breakpoint in your processor and start running it. Platform management units, right, like system management, power management, functional safety, encryption and decryption blocks, temperature monitors, a trust zone, and high-speed connectivity, like display ports, USB, SATA, PCIe, Gigabit Ethernet, USB, CAN, UART, SPI, and so on. And within of the programmable logic part, are the block RAMs, the ultra RAMs, the higher denser RAM, right? DSP blocks, which has ALUs and multipliers and adders, high performance, high IOs, high density IOs, and general purpose IOs, high speed connectivity like transceivers, gigabit transceivers. PCI Gen 4 is hardened. Okay, so a lot of hardened blocks and availability of processing subsystem and programmable logic. Now the question is where all they will use this kind of thing, right? So say for example you are having some tasks, right? Okay, you want to do it in software which can be very expensive in hardware, and sometimes you want to perform some hardware task, right, that can be very slow in software. So there is a fine balance between what the hardware and software is used, right? So there is some kind of a hardware software co-design happening. Let's take an example, right? If you want to understand, right? So say for example you are doing a surveillance camera. Okay? So in a surveillance camera, right, whatever you are capturing in terms of the camera images can go to the programmable logic, okay, and using a streaming protocol, right, it can be processed and filtered on the fly. But once the data is processed, filtered, what you call compressed, right, the data can go through the processing system furthermore, okay, and can get stored into a hard disk, whatever are the relevant pieces. Or it can, using a human machine interface, right, it can give a beep or a sound if it finds that the processing has resulted in some kind of a maybe it has detected some stranger, right, in a surveillance camera kind of a system, right? So those are some things, right? There is a fine balance between what goes into the hardware in the programmable logic and what goes into the software in terms of this complete processing subsystem. Okay, so keep a note of this, striking the optimum balance in the system partition. So for large systems, this has become the norm, right? To purchase an FPGA which has got both, right? The processing system as well as the programmable logic. Next, we already discussed about RF communication based components. I will only flash the foil and go forward, right? Because you see, right, this is more and more integration is happening. Okay, you could have a artificial intelligence based neural processing unit tiles. Okay, Ethernet and high speed SerDes tile. I mean, I'm just flashing the foil to give you a feel of what the complexity start getting added into the FPGAs at this point in time. Right, you have gigabit transceivers, and this is the Agilex F tile. Okay, it's a hardened Ethernet which has a PCIe built in. It has a SerDes block with an embedded multi-die interconnect bridge. So on one side is an embedded multi-die interconnect bridge. So two tiles can actually join together. One tile could be a programmable logic part, and the other could be a F tile, and the third tile could be a processing subsystem tile, and the fourth tile could be a interconnect, heavy, intercommunication kind of tile, right? So to create a big multi-chip module, right? So those are all possibilities that we are seeing happening in the current time. Okay. Then we see a lot of, so now from current time we are going to little bit seeing in the future, right? We are seeing that there is a concept of a chiplet, okay, and a market is being created using FPGA tiles where the user can create their own application, okay, and their own application based hardened tile and attach an FPGA tile for flexibility. So you say that, okay, I have my application based tile and then I use an FPGA for flexibility along with a high speed memory, right? So that is what. So the intent is not to show you different types of chiplet examples, but the intent here is to show you that how FPGAs are fitting into these complex components, right? So that was the intent here, and this is like going more than Moore, right? Because Moore said things will double, but now I am putting 3 chips here, right? So it's like more than Moore. So you are seeing more flexibility, more application specific stuff that is happening. Okay. So with this, right, a lot of the discussion on FPGAs, evolution and all has been completed. But what we haven't talked about, right? Modern FPGAs, they require massive software to work, right? Imagine you have an RTL, right, and you want to map it into thousands of configurable logic gates, right? You need massive amount of software to be able to do that, okay? Which includes data entry. It could be in the form of block design, RTL, vendor IP, it could be hardened IP, integration, constraints for static timing analysis, IO constraints, multiple FPGA attributes, pragmas to be given to, allow how high fan out, allow clocking, all those kind of things, right? Compilation, elaboration, and synthesis related, things has to happen in the software. Okay, place and route has to happen in the software, and the final bit file generation.
So we have
So till now we have only talked about the FPGA
so I
should
just
have
wanted
this.
to give you an update.
Along with the
timing so that-
FPGA, always comes a massive software, and
Okay,
that
fine.
software
So
does all
once
these
you are
things,
done, you
right?
can just close
Allows
the
you
window.
to do data entry. It will compile the design, elaborate the design, synthesize the design, place and route onto the FPGA of your choice, and create a bit file. Okay, what it also has to do, the software has to yeah. Okay, okay. No, no, I'm already done. I'm already done. We are at the last. Okay, okay, okay. Yeah, thank you. So now what happens is you have to once the bit file generation is done. Now since it's very complex, right? You have to do a FPGA debug of the hardware design. Okay, and FPGA designs also require design verification. So along with the FPGA tools, right, you need a design verification tool, right, which again is a massive software, right? We haven't discussed about evolution of design validation on FPGAs with complex design running on MPSoC. How would you debug such a system? We haven't discussed about reconfigurable computing, which allows an FPGA architecture, right, which allows for partial reconfiguration of the design based on multiple scenarios. Okay, so say for example, in a wireless communication, you could have multiple scenarios. You could have 2G, 3G, 4G, and each of these may use a different bit file for the same FPGA. Right? You could have a structured FPGA, which is a midway to an ASIC approach. A silicon die is prefabricated, and user would only tape out metal layers for the chip. This methodology is used when you cannot financially tape out a full chip, but you have decent volumes to sell. Okay. So this actually completes the the webinar for today. Now let's go to some of the pointers, right? So I used Wikipedia, okay, for creating this file set. I've used some of the web-based materials that are there for creating this file set. Okay, I've also used the data sheets and handouts, right, from multiple vendors, right, which we have put here. But let me open one or two vendors, right? At least let me open, say, for example, Zinc UltraScale product selection. Okay, if we open this up, right, okay, you will see how a family of devices are getting created, and for all the applications here, right, starting from a car or games, something in the newsroom camera, something on the RF and communications front, something in military, something in data centers, something in surveillance, right? So multiple applications, they have got multiple classes of devices, CG device, EG device, EV device, and their own application process, graphics process, programmable logic, and what are the applications that it can support. Okay, so that would give you a feel, right, of what are the things, right, that are hugely getting integrated into the FPGA. Okay, so what started as a simple programmable logic array, right, is now getting into massive proportion, right? With the advent of large scale, very high scale integration, okay, and monolithic circuits and chiplets and MCM modules, multi-chip modules, and so on. Okay. So you can see here dual core ARM Cortex A53, ARM Cortex R5, right? PCIe Express, right? It has distributed RAM, ultra RAM, system logic cells in terms of K cells, right? So if you see ZU9CG, it has 600,000 system logic cells, and it has 548,000 CLBs and CLB flip-flops, right? So that is the level of integration that is happening, right? And they also give a lot of flavors in terms of the IOs, right? So you have many multiple types of IOs here, right? So high density IOs, high performance. So if you could see this comma, right? These are high density IOs, high performance IOs, right? GTRs or LVDSs, GTH, GTY, right? Which are all the high speed SerDes. So now you are seeing not just one number for an IO. You are seeing a comma number for an IO, where each of these IO are different flavors of the IO that are available in the chip. Okay, so that is also coming up in a very big way, right? As the things are improving. Okay, so the last one was Acronix FPGA chiplets, and I also, right, for team members, right, who are like just begin or learning to use the FPGAs, right? You can start with the introduction to digital circuits, hardware modeling using Verilog, and digital system design with PLDs and FPGAs. So these are free courses, right, from NPTEL, because our own teachers have created these courses. You will also find a lot of courses on the Udemy or Coursera and so on, which I would not be marking it here for because they incur some cost associated with it. Okay, so with this, right, I close the session from my side. Over to you, Rahul.
Thank you, participants. And like a special thanks to Mr. Joshi for those wonderful sessions. So this kind of webinars we will be having it every month. So you can subscribe our blog, and this webinar will also be available in our YouTube channel. You can visit there and you can have a look on it. So now coming to our offerings. So this webinar is brought to you by Chip. So this webinar is brought to you by ChipEdge. So ChipEdge was founded in October 2012, and it's managed by senior industry professionals. And we are into this industry for like 11 plus years, and we have trained more than 4,500 engineers. And we have like 150 hiring companies who we like continuously give students who have completed the programs with us. And for the programs, what we offer, we also do placement support. So these are the program offerings, what we give. So we give programs for students and freshers. So, and for professionals, working professionals, for enterprises, as well as for educational institutions. So for students, we offer internship programs, soft skills, and mock interviews. For professionals, we offer a digital and analog VLSI design circle. For enterprises, we offer customized courses for both freshers and rattlers. For educational institutes, we offer train the trainer program as well as certification program for students. So these are our live online weekend sessions. So we offer programs in physical design, design verification, and design for test. So these are our upcoming programs which are available in weekend. So design for test program is starting on 12th May. Physical design is starting on 16th June. RTL design is starting on 6th July, and design verification is also starting on 6th July. So in the chat board, we will be sharing the registration form link. So whoever is interested to join for this program, so you can register here, and my advisor will call you and guide you to how to take up the program. So next stop is we also offer offline classroom programs in physical design and design verification. This is a 6-month integrated internship program. So and also we are now offering exam, like we are conducting an exam We call it Chip Edge VLSA Admission Test 2024, which is CVAT 2024. This is a job-oriented VLSA certification program
anything
with placement assistance. And also we offer merit scholarships up to 80%, and also we also have pay after placement models. So the upcoming courses under this program would be physical design and design verification. We have our first batch starting 10th June and our second batch starting on 8th July for both the programs. So both of the programs, the training would be in Bangalore. It is a 6-month intensive offline course, and the admission test is held on 5th May. And this is the QR code for our admission test. So you can use your phone to scan this and you can register there. So, and also we will share the link of the registration link through the chat board. So whoever is interested, you can register there. And the eligibility criteria for attending this test is you should be in your final year of your engineering or a fresher, like maybe 2023 passed out, 2022 passed out, maybe a fresher. All right. So coming up is our multi-semester model. We have a duration which starts from 3rd semester to 8th semester. So 1st to 4th semester in MTech batch. The engagement model would be within the curriculum through electives, where you will be doing a 40 to 60. So the engagement model would be within the curriculum, where you would be doing 40 to 60 hours of course every semester. So the specializations would be design verification, design for test, physical design, and layout. So integrated internship model is 4 to 8 weeks of internship after even semester, which is 4th and 6th semester, and 12 to 16 weeks of internship in the 8th semester. And you will also have a project of industry relevant projects. Next is co-teaching method, where we will be engaging with the universities or colleges who are interested to join with us hand in hand and teach their students. So this is for UG and PG students along with the professor of the college. We will teach the UG and PG students, and we'll own the 100% ownership of the program. So delivery models is live online teaching and offline models for local universities inside Bangalore. So our next program is our internship models. So internship, we are offering 4-week, 8-week, and 16 weeks of internship. The engagement model would be offline, online as per the location. So VLSA specializations offered in this internship model is RTL design with FPGA, so design verification, design for test, physical design, analog layout design. The next offering is faculty development program. The program duration would be from 1 week to 4 weeks. The VLSA specializations what is offered is RTL design with FPGA, design verification, design for test, physical design, and analog layout design. So the registration link is available in the chat board. Like whoever is interested, like you can go there and register yourself. So next up is we have our VLSA self-paced courses. So these are the courses which is offered. We offer self-paced. This course is especially for working professionals who wanted to like upskill themselves. So this course can be learned anywhere, anytime. The courses offered are RTL design, design verification, design for test, physical design, synthesis and sign-off STA and LEC. So the upcoming courses what we have is formal verification, TCL scripting, and Python scripting. And this is the link for our self-paced learning platforms. So this link will also be shared in the chat board. Who was interested, like you can register there and take your course by yourself. And all the projects and labs, everything will be available there itself using, and you can just register then and start using it. So these are few of our on-demand self-paced courses, what we offer. So few of the courses are like automatic test pattern generation and scan insertion and scan compulsion with OCC, synthesis using design compiler, and introduction to BIST, system Verilog essentials, system Verilog acceptance. So and these are also a few of our other courses: essentials of Linux, digital design, CMOS device and technology. All right, so the link which will be shared in the chat board, you can just go into that link and you can view all these courses and you can purchase it and you can start learning at your own pace. So these are our partners. So we have our own services companies, which is Celtron Semiconductors. And also we are partnered with India Electronics and Semiconductor Association, and we are an EDA partner of Synopsys. So all the programs which is taught by us will be under Synopsys Labs. So these are few of our hiring partners. As I said, like we have 150 hiring partners with us. So these are few of our hiring partners: HCL, L&T, MediaTek, Synopsys, and Metagraphics, AMD. All this are. So thank you so much thank you so much everyone. This is my email ID and this is my contact number. So anybody who has any doubts or any clarification regarding the admissions or process of admission, regarding the scholarship exam, regarding our program offerings, or if somebody is from the university who wanted to partner with us for co-teaching, you can contact me. So I will also put my email ID and number in the chat box shortly. In case of anything, you can contact me directly. So this was a wonderful session, and this session will be uploaded in YouTube shortly. And whoever wants to share it with your friends, you can share it with your friends. Or if you want to rewatch the session, also you can rewatch it. And also we will be having this kind of sessions every third Saturday of the month, and you guys will be notified. So thank you so much, and I appreciate everyone who came here this wonderful morning in the Saturday to come and enrich your knowledge in VLSI. So I hope everybody enjoyed this session. So I hope this session went very well. Any further questions will be answered. You can post your questions. All right. So any further questions, you can just email me. I will answer you through the email, or you can contact me over my phone and WhatsApp. Thank you. Thank you so much. You have a wonderful day ahead. Thank you all participants.